Okay, so if this is a class about statistics, we're going to be answering statistical questions, but what are those? What's a statistical question? So we're going to talk about what a statistic is, which helps with this, but to just get a general sense of it, I'm going to give you a bunch of questions and think about which of those questions you could just give me the answer to right now, and which of the questions you'd have to do some math to figure out. You'd actually have to do some computations, because that often will help you figure out which one is which. So here's some questions. How old are you? Can you tell me that? Is there a number, or do you have to do some computations? How about how old are people who have taken this class in the last 5 years? Do dogs run faster than cats? Do wolves weigh more than dogs? How about, does your dog weigh more than that wolf? These are my dogs, and so maybe all four of them together weigh more than a wolf. Does it rain more in Seattle than in Singapore? Or what was the difference in rainfall between Singapore and Seattle in 2014? So there's a bunch of questions there, and hopefully as I was asking them, you were coming up with answers. But let's go back through them. So how old are you? That's not a statistical question. That's just a number that you can pull out. It's just data. Now, how old are the people who have taken this class in the last 5 years? Well, it depends what kind of answer you want to give. You could list every person who's taken the class for the last 5 years and then also list their ages, in which case this is not a statistical question, it's just another data question. But you could give a single answer, which maybe is the average of the age of everyone who's taken the class, and then we do start getting towards a statistical question. Do dogs run faster than cats? In that case, we're talking about all dogs and all cats. We don't know how many there are. We can't enumerate all of them. We can't measure how fast every dog and every cat runs. So here, we're talking about kind of general questions where we have to take a sample, and that's very clearly a statistical question. The same thing goes for the next. Do wolves weigh more than dogs? We have a bunch of wolves, we have a bunch of dogs. It depends on the dog, it depends on the wolf, but you can come up with a general answer, but that's a statistical question. Does your dog weigh more than that wolf? Well, then we have a specific wolf and a specific dog, and so all we need to do is weigh them and compare, and that's not a statistical question. Does it rain more in Seattle than Singapore? This is statistical because we have to figure out what periods of time you're looking at, probably take some averages. But what was the difference in rainfall between Singapore and Seattle in 2014? That's a specific question. We can add up the amount of rain for each year and then just compare them. So that's not statistical. And so that's the general idea. A statistical question is one where there's not a precise answer. You can't just look at a piece of data and have the answer. That's because generally you have a population and there's variation in that population. And so you're trying to characterize a population where not everyone is the same. So how tall are human beings? Like, we're around 6 feet tall, right? Some of us are way shorter than that. Some of us are a lot taller, but we're characterizing the population with an average, which is useful if you want to say how tall are human beings compared to mature oak trees, right? We know that they're shorter, and you can get an idea of how shorter with those averages. So that's thing number one. Statistical questions have variation in the population, and you're trying to characterize the population. The second is that there's uncertainty because you can't measure everyone in the population. So do dogs weigh more than wolves? To answer that, even with averages, we'd have to take every single wolf and every single dog to get the average, which we can't do. So we actually have to sample the target population, and that gives us some uncertainty. Did we make a good sample? Did we happen to take a really big population of dogs and small population of wolves? So there's uncertainty. That's important for a statistical question. There's also statistical questions that look at the relationship between two or more variables. So, for example, you may want to compare height to weight. Are taller people heavier than shorter people? Again, there's variation among people, and there's uncertainty. What counts as tall versus short people? So this is a statistical question. We may also want to look at the relationship between something like sex and height. Sometimes you just want to know if those two variables co-vary with each other. So as height goes up, does weight go up? Other times we're interested because we believe one thing causes another. So does your gender cause you to be taller? If you're born male, does that cause you to be taller than if you're born female? Now, statistics are not always going to give us causation. In fact, most of the time they won't, but sometimes we can make those conclusions. But when we're looking for those kinds of relationships between populations where we have this variation and uncertainty, those are also statistical questions. Okay, so what we're going to be talking about in class is inferential statistics. There are descriptive statistics, and those are used to describe a data set that you have. So you may have the age of everyone in the class, and in that case, a descriptive statistic would be something like the average age of people in the class. You have the full data set, and you're describing it. An inferential statistic measures a sample, it infers values of parameters, and those are measures on the population. So essentially you're using a sample, a subset of everyone who could possibly be in the population, and you're using that to infer other data about the population. So for example, I might want to know, does greater student engagement in MOOCs predict greater learning? And so I use that to form a hypothesis or a testable research question. So my hypothesis is that if students are more engaged in a MOOC, an online class, that it predicts that they learn more. And so if we want to turn that into something that we can analyze with inferential statistics, the first thing that we need to do is operationalize it. And what that means is that I take this vague concept like student engagement and greater learning, and I convert it into something that I can test and measure. So with statistics, you have to have numbers, you have to have something to measure. And so something like student engagement or learning aren't measurable by themselves. We need to find a way to actually measure those, and that becomes our operationalized hypothesis. So for student engagement, there's a bunch of things that we could measure. We could look at how many times they actually log into the MOOC, or how many videos they watch, or how many questions they ask in the forum, or how much they participate in forum discussions. So there's a bunch of different measures. We have to pick one of those. And then we have to do the same thing for learning. How do we measure learning? So you could look at their final grade in the class, the average score that they got on their assignments, their final overall weighted percentage. Again, a bunch of things that you could do. So for us to operationalize this hypothesis, we need a way of measuring engagement and a way of measuring learning. I'm going to operationalize this by saying, do students who ask questions in the class forum have a higher final grade in the class? So that's the way that we're going to operationalize this. Once we've done that, we actually have to specify what our variables are. So a variable is a property of an object or an event, that could be a person, and it takes on different values. So in this case, our variables are who asks questions and how many questions do they ask, and what's their final grade in the class. There are two major categories of variables when you're asking an inferential statistical question: the independent and the dependent variable. The independent variable, in this case, who asks questions, is something that predicts the outcome. So it's the input, and we're going to analyze how that varies to predict something. In this case, do they have the final grade? So these are sometimes called predictors. They're the independent variables, and they're the things that we think may be related to the outcome. Sometimes we think that they cause it, but it doesn't necessarily have to be a causal relationship. It could just be that there's a connection. The dependent variable is the final thing that we're measuring. It's the outcome. We often think that outcomes are caused by changes in the independent variable, but again, that doesn't have to be true. There can simply be a connection between them. But often you'll find yourself asking, do changes in this independent variable cause changes in the dependent variable? And even if you can't prove that causal relationship, it's a good way to help you remember which is independent and dependent, because those terms are kind of easy to confuse. So in this case, we're going to measure, do students ask questions, and we're going to measure the final grade. The independent variable is who asks questions, and the dependent variable is the final grade. So now that we've determined what our variables are, we have to determine the scale that those variables are on. And there's 4 that we're going to talk about. Each one inherits the properties of the one before. So I'm going to give you all 4 of them. And we're going to start with a nominal scale. So this is basically a set of labels or names. You can see that they kind of fall into categories here. So where do you live? What's your hair color? What's your gender? You're kind of picking from a list. The next option is an ordinal scale, and here there's an ordering or a ranking of the labels or names. So how do you feel today? Are you very unhappy, just unhappy, okay, happy, or very happy? There's no requirement here that the difference between each subsequent values are the same. So maybe the difference between very unhappy and just unhappy is really big, but the difference between unhappy and okay is kind of small. So they have to be ordered, but the gaps between them can be of varying sizes. Next is an interval scale, and the benefit of an interval scale is that you have equal distances based on equal differences. So for example, if we're thinking about time, if there's a 10-minute gap, so the time gap between 12 o'clock and 12:10 is the same gap between 1:15 and 1:25. If the difference is 10, it represents the same distance or the same difference, whereas that's not necessarily the case in the ordinal scale that we were looking at. The issue with interval scales is that they don't have a true zero. So with time, we can, even using like the Unix time, which is a number of milliseconds since January 1st, 1970, like that's an arbitrary zero. There's no real zero for no time or the beginning of time. We could maybe go back to there with some fancy physics, but we're not there. Like generally, there's no zero for time. You can pick an arbitrary zero, but there's not like a true actual zero. And if you want a true actual zero, you need a ratio scale. So it has all the properties that we've talked about so far. Equal intervals or equal distances between values represent equal differences in value. There's a rank ordering, but there's also a true zero. So for example, a scale where you weigh yourself, there's 0 pounds, and that's a true zero. The same thing with temperature. Temperature is often used as an example of an interval scale, but with Kelvin, there's an absolute zero. You can't go below that. That's when all particles stop moving. And so that has an absolute true zero. The same thing for like a speedometer on your car, where you're looking at miles per hour. There's an absolute true zero. And so that's a ratio scale. The statistics that you can do vary between one scale and another. For example, an ordinal scale where you just have a rank ordering but you don't know the difference between values, you can't really compute an average. You could go ahead and try to compute it, but it's not really meaningful because if there's a big difference between one set of values and a small difference between another, you're not accurately capturing that by computing a mean. If you have an interval scale though, then you can compute a mean. So we'll talk about what values you can compute based on what kind of scale you have as we continue. Okay, so now that we've defined our hypothesis and defined our variables, the next step is to determine the study design and to gather data. So there's 3 different types of study designs. The first is an observational study. That's where you take 2 different groups who are kind of naturally separated and study them. So you could imagine having women over 50 who are smokers and non-smokers. Those would be your 2 populations. You haven't done anything to create those people into those different groups. They just naturally have separated out that way. So the good thing is that lots of this data is available where you can look at natural variations between groups. The bad thing is that you don't know what the confounding variables are. So say that smoking is your independent variable and your dependent variable is lung cancer. So you want to see, does more smoking lead to more lung cancer? Well, if you look at non-smokers and smokers, then you have your independent variable of whether they smoke, and your dependent variable, do they get more lung cancer, is something that you can measure. The problem is that if you want to draw a conclusion that smoking causes more lung cancer, you can't necessarily do that because you haven't controlled for things. So you may know that smokers have higher rates of lung cancer, but you don't know that smoking has caused it, because it could be, and there's actually a hypothesis, this is called Fisher's hypothesis, that some people have a gene that causes lung cancer and other people don't have that gene. That gene also causes you to be more susceptible to smoking. And so if you have that gene, you're going to get more lung cancer because of the gene. But the gene also causes you to smoke, and the smoking may have no impact on your chances of getting cancer. Now, we know that that's probably not true, but if you're doing this kind of observational study, you can't rule out those kinds of factors that are going to impact your design. So it's good to have naturally separated groups and you can describe them, but causation or understanding what variables are actually at play can be really tough. The next kind of study is an experimental study. In this case, we look at differences between populations related to some variation that we create. So we systematically control this. We separate people into groups. Hopefully we control for all these kind of confounding variables that might happen. There's some that we may not know about, and so nothing is perfect, but ideally we try to create groups that are systematically separated so we know everything's kind of the same between them, and then we look at the differences. There's also something called a quasi-experimental study. And so here we're looking at differences between populations again, but these differences are due to variation that's caused by some unrelated source. So for example, we may have people put into, say, 2 third-grade classes. So we didn't cause them to go into those groups, but it's not a natural variation. They were probably randomly placed in there. So there are differences, and we could say try one learning method with class 1 and one learning method with class 2. We can do an experiment in that way, but it's quasi-experimental because we haven't controlled who ends up in each population. It's just a naturally occurring group. So those are our 3 types of study designs. Experimental studies are the best, but they're also expensive and hard and take a lot of time, and so often we end up doing other types of studies. Once you have them, you want to think about what are the populations that you're going to look at, what are the parameters, what are the samples, and what are the statistics. So let's look at it with puppies. So imagine that you have all the puppies in the world. They don't all fit in this picture, but there's a lot of them. That becomes your population, all the puppies. We want to measure some statistic about the population. So say the average size of an 8-week-old yellow lab puppy. So here we have a whole bunch of yellow lab puppies. All the puppies are the population. We want to measure their average size. That size, the true average size of all 8-week-old puppies, is going to be our parameter, and that's true for the population as a whole. It's basically a thing that can't be measured because you can't get every puppy. There's new puppies being born all the time. So there is some theoretical average, but you can't really compute what that is. Instead, what you have to do is take a sample of puppies and compute the mean for that sample. So in the sample, you take a subset of all the 8-week-old yellow lab puppies, you compute the average weight for them, and that becomes your sample mean. And in inferential statistics, we infer that the sample mean is representative of the population as a whole. But when you do that, you need to think about how are you actually taking the sample. So this step, going from the population to the sample, how do you do it? There's a few different ways. You can do random sampling. So in that case, it's not just that you're picking without guidance. You're picking to ensure that each member of the population has an equivalent chance of being sampled. So if you were to do this with yellow lab puppies, you would want to find all the yellow lab puppies in the world that exist at 8 weeks old at this point in time, number each one of them, say 1 through 1,000,000, and say you're going to take every 1,000th puppy. So every puppy who ends in 000, you're going to take and put into your sample. So that ensures that you have equal distribution across all kinds of geographic regions, different parents, different lineages, and so on. That's really hard. Ideally, you want to do a random sample whenever you can because it gives you much greater validity to say that your sample mean represents the population, but it can be really hard. What we often see is something called convenience sampling, where you take a subset of the population that it's easy to you as the researcher to get. So if your friend just had a litter of 8-week-old puppies from her dog, you might take all the puppies from that litter and those become your sample. That's really convenient. If you happen to have this big room full of puppies on staircases, you may take the ones that you could grab that don't run away and put them in your sample. Convenience sampling is how the vast majority of research in the social sciences and information science and computer science tend to be done. You'll have students come in and take a psych study. There's an awful lot of psychology done on college students, right? And we generalize to the population from that. And you have to consider what impact your sample has. You have to report what kind of sampling you do. When we consider that the way that we've sampled may impact the results, we're talking about bias. So college students are definitely, there's a lot of bias in that sample. So if you're trying to conclude things about psychology in general, if you have a bunch of college students, there's an awful lot that's different about them, right? One, they tend to be clustered in a really tight age group. They tend to come from a certain socioeconomic status. Not each person comes from a, say, middle or upper class background, but they tend to be more from that group than others. They tend to have certain kinds of upbringing. They tend to have a certain level of intelligence. And so that can affect all kinds of things that you measure about their psychology. So there's bias in that sample. Sometimes you can't quantify what the bias is, but it's worth discussing when you're talking about what your sampling mechanism is. So to do inferential statistics, that's step 4. You actually apply your statistical measures and you use that to address your research questions. So you take your sample, you compute the sample mean, and the statistics that you get there, you use to come back to your original hypothesis.